Thank you, Melissa, and good afternoon, everyone. Mauricio Arias from the University of South Florida, and Willie Moa is from the Milwaukee School of Engineering. And
hello.
So, yeah, we've gone through this really cool adventure in coming up with this module, focusing specifically on the Bernoulli equation. If you don't remember this equation, we will show it at some point today. And if you go through our model, you'll see it multiple times. Yes, we're happy to say that we have completed the module. We already got some great feedback from Emad and Doug, and we're going through those edits right now. We here include the link to the module for you to follow that and hopefully use it once it's available soon.
Right, and you can see the screen, right? The presentation right now, or not? Yes.
We can.
Okay, great. Okay, so we will go over today the contents of our presentation today. We're going to cover the context of the learning module, what its key features are. We'll talk about the summary learning outcomes, not the detail, but generally overall what we're asking or what we're hoping the students come out with. We'll talk a little bit about the format of the learning module, what kind of features, how we're doing some presentations, and then we should have time for questions.
Okay, so a little bit about the context of this course. If I can just maybe get a few hands there on who has taken fluid mechanics as part of their engineering degrees or non-engineering degrees, just for fun. Not for fun. Okay. Yeah. To Freddie's point, it's very important. It's typically a mandatory course for all civil, environmental, mechanical engineers, maybe architectural engineers too. Willie, correct me if I'm wrong. And chemical engineers take their own form of it. So it's one of those courses that we all went through it. We know better, and in many cases, it was the first time, or for most engineers, it's the first exposure that we had to water. And in my case, that's really what kind of got me into this field. For other people, maybe that's what took them into something completely different. So when students take this class, they have a very little formal background in the subject, but most people taking this class, they're kind of upper, their second sophomore semester or the first semester of their junior year. Of course, for Will, it's different because they got quarters, so it's somewhere in between those around between the sophomore and junior year when students are taking these classes. We decided to we thought that the Bernoulli equation covers about maybe a third of what's covered in this class. We looked at the general energy equation. That covers probably more like about half of the class, and that's the equation that is written down below. For those of you who do not remember, the Bernoulli equation is specifically those components that are squared in red. So we decided to focus on that aspect now, and the idea is that eventually we can develop further modules on that content that needs to go before to completely learn everything you need to learn to apply the Bernoulli equation, and then the kind of follow up on the general energy equation. Okay. The idea is that the module will take about the same time that what is covered during the class. So that's anywhere between 8 and 12 hours. 2 to 3 weeks sort of. That's the main context related to this module.
All right, so key features of this learning module, we have authentic learning activities. Now, it's a little bit difficult to come up with authentic learning activities for the Bernoulli equation because the Bernoulli equation describes a situation that does not exist in viscid flow. If we did have viscid flow, people could make a whole lot of money because water could be transported without energy loss. But the Bernoulli equation does have a lot of good applications where we have close to viscid flow. We present a number of background for a number of real-world applications, and we use quite a few different teaching methods in this learning module, and it is filled with check your understanding quizzes and example problems. The example problems are to bring the students to the formula application level. Remember, this is an introductory level class, so we have to teach people how to use formulas. But then we do have learning activities that take students a little bit deeper.
So here's a quick summary of the learning outcomes that we expect students will be able to achieve at the end of this module. First is to, as a kind of entry-level class, is to remember key concepts about the Bernoulli's equation. If anything, be able to write it down. Also to demonstrate the ability to solve any missing variable in the Bernoulli equation. I think that's how most of us learn how to apply the equation. Then be able to apply the Bernoulli equation to an unfamiliar authentic situation, and also apply the equation to an authentic problem, specifically related to water infrastructure design and management, which is maybe what brings us all here together with how to learn. I'm going to let Willie tell you guys a little bit about the background of that picture to the right.
I was in consulting engineering for 25 years, and when we would have newly graduated engineers coming for their first job out of college, I would often ask them during the job interview, why a shower curtain blew inwards when you were taking a shower? And if the students could come up with a reasonable answer, and oftentimes I'd have to help them, that would be good. I remember one time a student said, I had a really bad fluid mechanics professor and I really didn't learn anything. Well, that one wasn't hired, that particular student. So actually, we do present this challenge question at the beginning. Why do shower curtains blow inwards when you're taking a shower? And hopefully by the end of the learning module, the students can give a pretty good reason why.
And then to follow up to that is that so we start the course with that kind of an application, and then we end the course with a culminating video where students are asked to demonstrate in a video how fluid mechanics kind of applies to their daily life activities. And but we're really hoping that nobody makes videos in their showers.
Right. So the format of our model, this one's mine, remember? Okay, the format of the model is an introduction where we go over the basics of the context of the course and what the actual learning objectives are. And then we have 4 sections: the development of the Bernoulli's equation, and then we develop the continuity equation and combine it with the Bernoulli equation, and that is quite useful. And then we go over hydraulic and energy grade lines, which is a pictorial way of mapping how energy changes. And the Bernoulli's equation is really just a way of expressing the energy in the system. And then we finish up with section 4, where we have different applications of the Bernoulli's equation. We'll go over the introduction and those 4 sections.
Okay, so the introduction, we start with the overview of the module, what's being covered, how long it's going to take, all that good stuff. We also present the 10 learning objectives for the entire module here. And we make quite a bit of emphasis on real world applications. I think this is something that could make a big difference for those of us that that decide to go into the water career, or those that kind of give up and really hate fluids. So we always try to make that connection to real world applications, and we start that from the very beginning.
So we present this one slide right here, and then actually during the learning module, we cover most of these applications that are shown in this real world applications summary slide. So section 1, development of the Bernoulli's equation. Of course, we introduce it where we talk about the specific learning objectives. I believe there are 4 learning objectives with the development of the Bernoulli's equation. We introduce that, and then of course we have to derive the Bernoulli's equation. There are various ways of deriving the Bernoulli's equation. We go from Newton's second law. That's how we derive it, and we derive it both kind of like a textbook derivation where the students read it, but then we also present a video derivation of that. And then after deriving it, we help the students interpret that. There are three elements. There's the pressure head, there's the velocity head, and there's the elevation head. So we give the students examples of those 3 types of energy so that the students can grasp what the Bernoulli's equation actually is. And then we do a learning activity number 1. At the end of each section, we have a culminating learning activity, and we use the Bernoulli's equation to explain sediment transport in rivers. Sediment transport in rivers is a big deal. We spend in the US billions of dollars dredging harbors and dealing with sediment transport. And we use a relatively simple model of sediment transport where you have water velocity above the particle, which creates a lift. There's no velocity below, and it can lift up those particles and cause saltation. So we actually show the saltation. We give a couple of videos to give an idea of what this means. Saltation is jumping. Saltar, the verb saltar in Spanish is actually to jump. So that's what we're doing. We give this example to the students, this saltation, and let me let's see. All right, got to get out of this here without. Okay, what do I do right now to get back to the meeting? Because I think you can't see what I need to.
You have to go to the tab, right?
Yeah, but I've got this thing in the way. Let me see if I can go. Here we go.
Bingo.
I'm back there. I was able to get there. So that is section 1, development of the Bernoulli's equation.
Excellent. Okay, so once we cover the Bernoulli equation on its own, then the section 2 focuses on combining the Bernoulli equation with the continuity equation. And as most of the actual implementations or applications of the Bernoulli equation, you have to use the continuity equation where you relate velocity and the cross-sectional area of the flow to the volumetric flow rate. So we first derive the continuity equation here, and then we explain how we combine that equation with the Bernoulli's equation. For that, Willie actually recorded a very nice video here of the derivation of obstruction flow meter equation. We're not going to watch the 8 minutes of it. We're just going to quickly show that.
So this is like in-class board work. This is one of the learning methods we do. It's in-class board work, but it's done right here in the context of the learning module. Back to, there we are.
All right. And then finally, at the end of this section, we have a learning activity that focuses primarily on the continuity equation. We're exposing students here to sizing pipes. And the kind of the context of this problem is a fictional town called Happyville, where there's a runoff, a stormwater runoff being collected and is being sent to the stormwater treatment wetlands. We give the students you know, a maximum kind of design flow for the treatment wetland of 10 million gallons per day. Then we give them the length of the pipeline, which is half a mile. We ask them, and then we also give them a velocity constraint. Forgot the exact number here right now. It's, you know, pretty broad, between 1 and I think 6 feet per second. And so based on that criteria and that range, we're asking students to come up with the best combination of pipes. So what, you know, how many, you know, what's the optimal diameter of the pipes? How many of those pipes? And then what is the cost of those pipes? And we give them a table with a range of prices for PVC pipes and concrete pipes.
Section 3, hydraulic and energy grade lines. Of course, we have the introduction where we give them the learning objectives, and then we actually have to define and give examples of the hydraulic and energy grade line, exactly what that is, and then describe to the students why it's useful. Here you are, you're hand drafting the total energy and the piezometric head in the pipes. Why is it actually useful? So we actually spend some time doing the utility, and then we came up with a learning activity of drawing and using a hydraulic grade line to improve a water distribution system. Now the challenge with doing energy grade lines when you're looking at Bernoulli's equation is you have no losses. So there is no energy loss, so it's very flat. It's only once you get farther along in the general energy equation where you're dealing with energy loss that hydraulic grade lines and energy grade lines make more sense. So it's kind of a challenge to come up with an authentic real world module, but actually when the water in the pipes is not flowing, there's no energy loss. So we have a system where this is an actual pipeline that I was involved in working on many years ago, earlier in my career in Eastern Panama. And we needed to break pressure because the pressure was too high. What you see here is the solution to the learning example where the students have to draw different minimums and maximums of pressures and interpret the hydraulic grade line and the profile of the water pipeline. It's a very good real world application. We introduce the students to how we actually develop those profiles, and those plan and profiles are those plan and profiles are very useful in civil engineering. I'm going to stop this. What's interesting about this is, although we're not teaching students how to use Google Earth Pro, we're showing the students a use of Google Earth Pro, and then the students are going to have it in their head, oh, I can get information from Google Earth Pro because I remember seeing that in a learning module where it was not part of the learning objectives at all. It was just a tool we use as engineers to develop hydraulic and energy grade lines. And this, by the way, is a real authentic problem that I was tasked to solve in the mid-1990s, actually.
Okay, so by at this point in the module, the students are experts on the Bernoulli's equations. They can, they probably can repeat it out loud in their dreams. So what we do at this point in this final section is present some applications to the Bernoulli's equation, right? So, and there are many of these applications. We focus on three kind of textbook cases. One is pitot tubes, like the ones are used for to measure altitude in planes. We also study cavitation, which is very important for civil engineering and mechanical engineering applications. And we also look at flow from tanks or reservoirs. It's also very important. Here is one demonstration that Willie carried out in the lab. I guess right before we started doing the module, so that worked out very nicely. So yeah, here's the demonstration of the flow from the tank. And then, so, we give students this kind of example, and the idea and the culminating activity of the module is we ask the students to come up with their own experiment, all right, where they have to, in that video that Will showed, he actually explained some of the dimensions and why water doesn't go exactly where it's supposed to go and all that. So we ask students to come up with their own experiment, as if they were quarantined in their house. So, with whatever materials they have, no fancy tanks or meters or anything like that, just with whatever materials they have in their house or whichever scenario they prefer, they have to come up with their experimental design and demonstrate that to the class. So I've given that assignment before to some of my students. So here's one example of some students last year who made this video about the Bernoulli's equation, some applications for just water going through this magic hose here. And this is our kind of the culminating activity. Here's where we have a detailed rubric that we go through to evaluate students.
All right, that is the end of our presentation. We do have, we're ready to take any of your questions now.